Today let us prove that element stiffness matrix is given by dTdB at volume integral into dV. Let us prove that. Where B is the strain displacement matrix, D is the constitutive matrix, and K is element stiffness matrix. So let us show that or prove this relationship using the knowledge or whatever you have acquired so far in the finite element analysis. First, we know the displacement at any point in an element, in a finite element, is given by the relation relationship, the displacement Q at any point I in the element is given by the shape function into element displacement, nodal displacement vector. This we have already seen while deriving the shape functions of various finite element, where n is shape function, and Q is element nodal displacement vector. Element nodal displacement vector, that is of course in the local coordinate. So also we know the strain at any point in the element, so that is denoted by the symbol epsilon E. At any point, epsilon I is given by the relationship epsilon I is sigma, or the change in the displacement by original displacement, or we can also indicate it by the symbol QE, where QE is the nodal displacement, element nodal displacement, and strain D is the strain displacement vector. So consider a one-dimensional element. Consider a one-dimensional element in nodal coordinates, in element coordinates, or in global coordinates, and as well as natural coordinates, as in figure element 1, 2, one-dimensional element 1, 2. So the natural coordinate, it will be measured from the center point of the element, and it is denoted by the symbol psi. Here psi is equal to -1, here psi is equal to +1, and the displayed shape functions of this is in natural coordinates. Natural coordinate. So in global coordinate, treating this element as isoparametric, right, it will assume the arbitrary shape, as I told you in the previous class, the isoparametric element. So this assumes some irregular shape like that, 1, 2, in that particular fashion. So this is global coordinate. Here x is equal to x1, here x is equal to x2 at the coordinate 2 in global coordinates. This is in natural coordinates, this is in global coordinates. So assuming element to be isoparametric, assuming the element to be isoparametric, the coordinate at any point x is given by n1 x1 plus n2 x2, where at any point the coordinate x coordinate is given by shape function at node 1 into x1, shape function at node 2 into x2. This is isoparametric formulation where x is given by 1 minus psi by 2 into x1 plus 1 plus psi by 2 into x2. So the Jacobian matrix J is nothing but delta x by delta psi. That is given by, from this, delta x by delta psi is minus half into x1. If you differentiate this with respect to psi, you will get differential coefficient of this 1 minus psi by 2 as minus half into x1, then plus half into x2, or this is given by x2 minus x1 by 2. That x2 minus x1 by 2 is nothing but the length of the element. The x coordinate minus here x coordinate of 2 minus x coordinate of 1 is nothing but L by 2, where L is length of element. So therefore Jacobian will be L by 2, or Jacobian inverse, that is nothing but delta z by xi by delta x, that is 2 by L. This is the important relationship between the natural and global coordinate system of isoparametric pattern formulation. Jacobian is the matrix which relates the element in natural coordinate system to the element in global coordinate system. So when once you know the Jacobian inverse, then you can say we know strain, not strain, displacement. Displacement at any point in the element, Qi is the displacement is given by NQ. NQB, this is from 1. Know that. Therefore, strain is equal to delta Qi divided by delta X. That is first derivative of displacement is called strain in the case of one-dimensional element. In this relationship, strain epsilon I is given by this. This is nothing but delta n by delta x into 2e. This delta n by delta x, you can write it as delta n by delta xi into delta xi by delta x. Value is not altered. Delta n by delta xi, delta xi by delta x, delta xi cancels, it will be delta n by delta x only into 2e. So delta z by delta x is nothing but Jacobian inverse, or this is equal to 2 by n into delta n by delta xi into QE. This is the relation. So now you substitute for delta n by delta xi. Delta n by delta xi is nothing but delta by delta xi of 1 minus xi by 2, 1 plus xi by 2. So that is, or this epsilon I is equal to, this is delta n1 by delta xi, then delta n2 by delta xi, because n is n1, n2. Here n is nothing but n1, n2. N is n1, n2, n matrix. It's a 2 by 1 by 2 matrix. This is 2 by 1 matrix. Q is nothing but Q1 and Q2. Displacement at 2, displacement at 1. So this QE is nothing but Q1, Q2 vector. That is 2 by 1 matrix. N is N1, N2 matrix. So you can multiply it easily. So this will be 1 by 1 matrix, that is Q. Displacement at any point. So N is N1, N2. Here delta n by delta xi is given by this into QE. Of course, 2 by L is there. Epsilon I is equal to 2 by L into delta n1 by delta xi, delta n2 by delta xi, because n is nothing but n1, n2. So this is again 2 by L. This is minus half, this is minus half. Because n1 is 1 minus n by 2, n2 is 1 plus n by 2. If you differentiate 1 minus n by 2 and 1 plus n by 2, you will get this. So, or this is QE, or these two to get cancels, or you can take epsilon I is nothing but 1 by L into minus 1 into QE. into QE. That is what I have told here. B into QE epsilon. Epsilon I of this element, here epsilon I, the element is given by B into QE, where B is 1 by L minus 1. After knowing this much, this you call it as the relationship to. So whatever relationship I have told for Qi as well as epsilon, I have derived and shown here. So because this of course you know from your already some fundamentals. Displacement at any point is given by shape function into its nodal displacement. Similarly, this strain is given by BQE, this relationship. This I am calling it as 2. So this relationship I have derived from the isoparametric concept. But this I have considered the example of one-dimensional element. So I have shown this epsilon I can be written as B into D, where B is given by 1 by L into minus 1, which is a constant quantity. And B is called B is nothing but strain displacement matrix. Of course, as the name itself indicates, it is the matrix which relates strain with the nodal displacement. Q is the nodal displacement. When once you know the nodal displacement relationship which has been related with shape function with the nodal displacement, B also can be determined from this. So now we will take up the general potential energy. So after knowing this, we know, and also we can say stress at any point. Stress at any point in the element sigma I, in the element is, when once you know this strain at any point, stress is strain multiplied by E or B, where B is constitutive matrix. Constitutive matrix. This is from elasticity. It is nothing but stress strain. D, of course, in one-dimensional element case, it is E, Young's modulus of elasticity, which is equal to E for 1D element. It is relationship between stress and strain. Relationship between stress to strain is called constitutive matrix. Of course, for one-dimensional matrix it is E. So this is relationship 3. So we have 3 relationships now. Q is equal to ND, Q in any, at any point of the element. Strain at any point of the element is given by B into QE, and stress is given by epsilon ID. So we have now the general relationship Q at any point is given by N into QE, nodal element displacement, and epsilon I is given by B into QE, that is relationship 2, this is relationship 1, relationship 2, then sigma I stress is given by constitutive matrix into strain. This is the third relationship. So I have just shown that for an isoparametric element, treating the isoparametric element concept that has the basis. So I have these 3 relationships. Because in the derivation they have asked usual notation. Usual notations are this, that is D, B, N. N is the shape function, B is the strain displacement matrix, B is the constitutive matrix, and of course Q is the nodal displacement vector. And these are the unknowns which you can get. All are functions of nodal displacement vector. Mind it. That is the one which you have to do. Because this epsilon I is nothing but D into B into QE. This B, epsilon I is nothing but B into QE. So all these three relationships are functions of QE, nodal displacement vector, which we have to determine. So for determining this, now we have to establish this relationship. For that, now we will just take the energy, potential energy in the element is given by phi is equal to, you know this relationship, that is nothing but strain energy of epsilon I element into, of course, transpose into sigma I of the element stress, where both are of same order. That's why when we are multiplying matrices of same order, I have to write one transpose of the other. So into dV, this is strain energy, internal strain energy, minus external work done, that is Pi of the element, nodal loads, because all loads we have to treat only acting at the nodal points. At any nodal point, what is the external load multiplied by the displacement, element nodal displacement, QE. That is your total energy potential. So whenever we are considering the element subjected to some external load, internal energy is there, external work done is there. This internal energy minus external work done, that we call it as the energy potential or potential energy. So then by you substitute, therefore phi is equal to, I will substitute the value of epsilon sigma from this relationship. That is nothing but half into epsilon is B Q B epsilon I, epsilon I is nothing but BT, epsilon ET, IET is given by BT QE. T transpose, that is for epsilon T. Epsilon I Et is nothing but Bt QET. Then sigma Et is B. Epsilon I is again this B QE. is nothing but sigma E, epsilon E I, Et is nothing but this into dV minus sigma Pi. This is your energy potential. So by principle of minimum potential energy, by principle of minimum potential energy, this delta of pi by delta of q v should be 0. By minimum potential energy is total energy potential first derivative with respect to the nodal displacement should be 0. If you take first derivative, first partial derivative of this expression, you will get that relationship. So now, here QET, QE, QT into QE is nothing but Q square. Because both are of same order, one transpose of the other. If you multiply this by, you will get Q square. So this we are differentiating partially with respect to QE. Therefore, for derivative of QE squared is nothing but 2QE. 2QE, that 2 and this 2 will get cancelled. So therefore, you have delta by delta 2y is nothing but this integral, volume integral, this dt dv, this remains same. This QE and ET transpose and QE is QE square. Partial derivative of that QE square is 2QE. That 2 and this 2 get cancelled. You will have only QE, QE into dV minus sigma of Pi. Partial derivative of QE is 1. Delta QE by delta Q is 1. That is equal to 0. Or I can write this relationship as KE. This I will call KE to E equals P. P is equal to KQ, stiffness matrix into nodal displacement. So here, this KE is nothing but dt dB which is nothing but the element stiffness matrix. Element stiffness matrix. So this is the derivation of this stiffness matrix of a one-dimensional element or any element for that matter is given by this expression dt dB, where B is strain displacement matrix, D is constitutive matrix. If you know these two, and of course B and D are from where D is constant, B is function of nodal displacement. So first you have to solve the nodal displacement from this relationship. After start determining this, then we can estimate the stiffness matrix. So that is this derivation. Now let us actually derive the same stiffness matrix for a bar element, stiffness matrix for a truss element in both local as well as global coordinates. Now next expression derive the stiffness matrix from a bar element so you consider a bar element like this in natural coordinates. The same thing you have to repeat. I have already taken example of bar element by deriving that general stiffness matrix. Here also again we derive it. So this is that element z is equal to -1, z equals +1, and this is in natural coordinates, bar in natural coordinates, bar in global coordinates are this. Which is that x, 1, 2, x is equal to x1, x equals x2. This is the global coordinates, global coordinates. This is length L, A, E, D, axial rigidity of the bar. Consider a ball element, consider a ball element in natural and global coordinates as shown in the figure. This is in natural coordinates, representation of the bar. This is in global coordinates, representation of the same bar. Strictly speaking, in the global coordinate, by assuming this as isoparametric element, we can assume any shape, arbitrary shape. It can incline in any fashion in space. But I am writing it in the same thing. But if you plot it or if you map it for first order bar element, it is of same shape. It is not going to change its shape. Whereas if it is a 3-noded one, then it will assume a curved shape in the isoparametric formulation. So I have derived a general stiffness matrix equation for a general isoparametric element. I have derived. Now I am specifically deriving that same equation for a bar element. It has been shown both in natural coordinate as well as global coordinate fashion. Strictly speaking, it is an isoparametric element. So all finite elements, we can treat them as isoparametric element, as shown in figure. Now, we know Q of the element at any point is given by N1, Q1 plus N2, Q2. Already have derived this. Where N1 is 1 minus psi by 2 and N2 is 1 plus psi by 2. 1 plus psi by 2. Where N1 because this function of the shape function of the shape functions. And of course, Q and Q2 are the nodal displacements. The same thing in here. Q2, Q1 of the node element when it is subjected to some load. So, there is a strain epsilon of the element. The strain at any point is given by delta Qi E by delta x. Strain is first derivative of the displacement, which is nothing but delta N1 by delta psi into delta z by delta x into Q1 plus delta N2 by delta z into delta y by delta x into Q2. I am differentiating this with respect to x. So when I am differentiating this, instead of differentiating directly, I am differentiating because n is a function of z. That's why this, when differentiating this differentiation has to be a function of x for relating with strain. So this also I have converted into z as a function of z. That's why I am writing this relationship. Already you know this is assuming this element to be isoparametric. So this is nothing but 2 by L that already I have shown by deriving the general. But delta z by delta x is nothing but Jacobian inverse. It is 2 by L. So therefore epsilon I is equal to delta m1 by delta z. It is minus half delta m1 by delta z is minus half. Differential coefficient of 1 is 0, minus z by 2 is minus half. So similarly, delta z by delta x is nothing but 2 by similarly, plus delta n2 by delta z is again minus half, not minus half, plus half into delta z by delta x is nothing but 2 by z equals, that is that. This into Q1 plus this into Q2. Delta n1 by delta z is minus half, delta z by delta x is 2 by L. Delta n2 by delta x is half, delta z by delta x is 2 by L. So this strain is given by minus Q1 plus Q2. Or this, I can write it in matrix form like this. Q1, Q2. This is minus Q1 plus Q2. That is same thing. This has written matrix form. So epsilon I is equal to BD. So therefore, epsilon I of the element is E into QE. QE, the element is Q1, Q2. Element, nodal, displacement, vector. So, then stress, don't bother about stress, straight away, epsilon I is no okay, stress at any point. This is stress at any point, sigma I in the element is given by d into epsilon. This is from the stress-time relationship. So we have K element stiffness matrix. Just now I derived. It is given by volume integral dt. Here, I already told A, D is equal to constitutive matrix for bar element. So therefore, this is nothing but, therefore KE was the, or that is volume integral dt. B is minus 1, 1. QE Q2 and B is this. B is 1 by L square, sorry, epsilon I is 1 by L, 1 by L, common factor, 1 by L into this, 1 by L, here minus 1 by L, 1 by L I have taken outside, 1 by L I have taken outside, this is minus Q1, this will be plus Q2, so it is 1 by L minus 1. You see that BT is 1 by L minus 1, I will write it as a column, transpose. Then D is nothing but E, B is nothing but minus 1, and dB is A into dx. Volume is area of cross section into length. The length at that particular point, small length. So then when I write this, of course I will retain as it is. In the next step I will write it. This I will convert it into a line element. This 1 by L minus 1 B minus 1 into A result. This is right. dB is nothing but, of course, A dx, A into dx, or this minus 1 to 1. Why this has changed to line integral means is dB I have converted into area into dx. Now we have to integrate it only with respect to length, not with respect to volume. It is only with respect to length. This dB expression I have changed it into area into length. Length means it is only have to integrate with respect to length. So this is nothing but 1 by, this is also 1 by L. I have forgotten. 1 by L into BT transpose is 1 by L into minus 1, and B is again 1 by L minus 1. So this is 1 by L. This is 2 by 1 matrix, 1 by 2 matrix. So this will be a 2 by 2 matrix. So minus 1, it is 1, minus 1, it is minus 1 minus 1, minus 1 into A, B, dx. Here I have B, here A is 1 by L, 1 by L square into dx. This I have, or this is A by L, or this I can take integrate it with straight away with respect to this, I will say minus 1 AE by L square minus 1 minus 1. That I am writing as it is. This dx minus 1 to 1. Dx is nothing but Jacobian relationship between natural length, that is 2 by L into dz. I already told x in the previous slide, that expression, that dx is nothing but L by 2 into 2 by L into dz. That already proved. And not L by 2 into dz. That is Jacobian matrix into dz. That's the relationship between that thing. this. So this will cancel. We will have AE by L into 1 minus 1 minus 1 1. This integral of this 2 I will take it here. AE by 2L minus 1 minus 1 minus 1 1, and integral d psi is nothing but sine. Limits 1 to minus 1. So 1 minus of minus 1 it is 1 plus 1 2. That 2 and this 2 will cancel. We will have AE by N into 1 minus 1. You see that stiffness matrix of a Bohr element. So first you have to write the displacement at any point in terms of shape function that will coordinate. Then you have to write expression for epsilon I, which is nothing but derivative of this displacement. Then you have to use the Jacobian relationship already I have here. So dz by dx is 2 by L, or dx by dz is 2 by L. Therefore dx is equal to 2 dz. We'll have dx is equal to 2 dz, that particular thing. This you reverse it, you will get that particular. This will be L by 2, this will be dx by dz. So therefore dx is equal to L by 2 into dz. That's what I have taken here. Dx is nothing but L by 2 into dz. So you will get this. So use the expression for Ke and you will get finally the Bohr element of the stiffness matrix. This much exercise. Knowing all that the expressions earlier, whatever you have studied here to shape function, strain, stress relationship, then also derivation of stiffness matrix element property, all those things, keeping in mind, you can derive the stiffness. This you can use for your practical problems. Next, third problem. We will take the stiffness matrix of a plane truss element for a, that is next problem, derive the stiffness matrix for a plane truss element. The difference between Bohr and plane truss element is plane truss element, it can assume any shape, any direction, whereas Bohr, it is always either horizontal or vertical. Even if it is inclined, load will be only along the axial direction. But in truss element, load can be acting at the nodal points first. It can be in any direction. So, and also it can be in any direction. So you consider a typical truss element. So consider a plane truss element. Here, 1, 2, as shown in figure. In natural, in local coordinate as well as in global coordinate. Incline at an angle theta in counterclockwise direction. Then the direction cosines, you can write it as L is equal to cos theta, M is equal to sin theta. The direction cosines of this plane truss element. Length is L, A is the axial rigidity. If you take the same element, after this is Q2, Q1, and in global coordinates, the displacements will be 2 per node. This U1, U1, U2. This is local displacement, local or natural coordinate displacement, natural nodal displacement, Q1, Q2 along the axis. This is global direction displacement. So you can say Q1 is nothing but U1L plus U1M. We have the relationship between the global and local displacements. Q2 is equal to U2M. Because this is theta, right? Q1 is this. This is Q1. This U1 into cos theta. U1 cos theta is U1L. This component, 90 minus theta, so this is cos of 90 minus theta is sin theta. So V1 sin theta, that is nothing but V1M. Likewise, U2L, V2M is Q2. This is just by direct emission. So therefore, the nodal displacement, the element nodal displacement Q1, Q2 is in the matrix form. Then write it as L, M, into U1, V1, V2, in matrix form. Q1 is equal to L into U1, M into V1, 0, 0. That is this. Similarly, Q2 is U2 into L, V2 into M, and 0 into U1, 0 into U1. The same thing I am writing in the matrix form. So this is 2 by 4, this is 4 by 1, this is the 2 by 1. So this is the relationship between the local as well as Cartesian coordinate system. This I will call it as U1, U2 is equal to this L matrix into U1, U1, U2. So this is what we have the relationship. So now, if you just take out the element stiffness matrix, I will just take it. So we have strain at any point, strain at any point, epsilon is equal to E into Q element. This already I have read. So epsilon E is equal to B is 1 by L into minus 1. That I have already derived in the previous sample. This QE is nothing but, I can write that, QE is minus L M, or I will write that QE as it is, so that it will be clear that like this. Q element is this. So all this I can write it as minus 1, 1. Now I will write this. This is L, M, 0, 0, 0, 0, This is 2 by 4. This is 4 by 1. By 1. This is 1 by 2. This, if you multiply, you will get 2 by 1. This is 1 by 2, and that 2 cancels. You will have 1 by 1 matrix. So this I can write it as 1 by L minus 1 into L minus L. 1 into 0, 0. Then minus 1 into m minus m. 1 into 0, m. Minus 1 into 0, 1 into l, l. Minus 1 into 0, 1 into m, m. So this is nothing but 1b into the global displacement vector. This I am calling it as Q. It is global displacement. Instead of just Q1, Q2, now I am transforming into global. So the new strain displacement matrix in global coordinates. That is, if you treat this as a strain element, not just a bar element in any direction, so it will have 2 displacements. So to convert that particular thing into global, this is what I have to do. So therefore, strain displacement matrix for plane truss element is equal to, in global coordinates, is given by 1 by L into minus L minus m, L, m. This you have to remember. In case of bar element, it is just 1 by L minus 1, 1. Now it is 1 by L minus m, L, m. And therefore, stiffness matrix, in global coordinates of this plane truss element is BT B. So this is nothing but I will convert this into line as it is. PT is nothing but is 1 by L minus L minus m, L, m. This is D. BT is changed, go to column. D is nothing but V, and D is 1 by L minus L minus m, L, m. That is D. And dV is nothing but area into dx. dx I will convert it into L by 2 into dz. The same way as I did for the bar element. This is minus 1 to 1. So we will get the expression for stiffness matrix for plane truss element. So, if you simplify this, it is A, E by, of course, this L and this L will go. We have only one single L, AE by L, 2L, AE by 2L, 2 is there, A, E by 2L. This I will multiply minus L into L. Minus L into minus L. So this is minus L. Minus L into minus L, it is L square. Minus L into minus M, Lm. Minus L into L, minus L square, and minus Lm. That is by multiplying by this first with the first element of the first row of this vector, and here all. Then again second you will get Lm. Then you have M square. Then you have minus Lm. Then you have minus M square, then minus A square, minus Lm, A square, Lm, minus Lm, minus M square, and Lm, M square. Because this is 4 by 1 matrix, this is 1 by 4 matrix. If you multiply, you will get a 4 by 4 matrix. That is the global stiffness matrix of a plane truss element. This is minus 1 to 1 of design. Correct? Design. So this again, integral design is Z. Upper limit and lower limit is substitute. 1 minus of minus 1. It is 1 plus 1, 2, the 2 then these 2 is cancelled. So we have the stiffness matrix and a plane truss element will be A by L into this. You remember, this is simplest way of remembering. First you write this L square, Lm, M square. You write that. First 4 element you remember. That you write. Then you reverse this sign. Minus L square, minus Lm, minus Lm, minus L square. Same thing you bring it here. Minus L square, minus Lm, minus Lm, minus M square. Here, the same thing. Whatever you write it. L square, Lm, Lm. But the easy way of remembering this, you just remember this 4. Then the same 4 you write it here. Then change its sign. So you can remember the general stiffness matrix. Of course, A by L. In case of power element, the A by L, 1 minus 1 minus 1. In plane truss element, because it is isoparametric element virtually. It has been written only in the global transformation of that stiffness matrix is this. Is it clear now? So unit 5, that's the last unit of your syllabus, derivation of stiffness matrix for plane truss element as well as beam element. Only 2 are there. Truss I have done, beam element also I will do it. That completes all the theory portion. Then using this, that is solve the problems. So now straight away, we will take some examples, problems. We will finish this plane truss analysis today only. Next we will take up B. And it is